Hi everyone. Today we are going to see about the topic batch and continuous cultivation kinetics. So what is batch and continuous fermentation? Batch fermentation is a closed process whereas continuous fermentation is an open process. So what do you mean by kinetics? So we all know about the batch fermentation and the continuous fermentation. So kinetics is nothing but the rate of any product formation. That is the rate of the how does the fermentation process moves on with respect to time. So that we are going to study for separate fermentation processes, batch fermentation and continuous fermentation, and how it is being calculated. So before moving into the topic, we need to know what is a system. A system is surrounded by many different objects and it has a boundary. So the system is being affected by the external surroundings. So batch cultivation is nothing but the bacteria is inoculated in the bioreactor. Then under certain conditions, the bacteria will go through four different phases like lag phase, log phase, exponential phase and stationary phase. But in the case of continuous cultivation, the fresh medium is continuously given to the organ or inoculum and the product is also removed at the same time. So the organism will not have any dead phase. It will be in the log phase throughout. So the bacteria is grown under certain conditions such as temperature, pH and aeration and it does not have different growth phases as in the case of batch cultivation. So advantages and disadvantages of batch cultivation include it can be used for different reactions every day. Sterilization will be proper and little risk of infection will be there, but the major disadvantages we have high laboratory cost, much ideal time and safety is very and cleaning process is very complicated. And in the case of continuous cultivation, the main advantage is low labor cost and good utilization of reactor, and it is very efficient due to autocatalytic nature of microbial reaction, and automation will be very appealing and constant product quality will be there. But the major disadvantages is continued production of months fail due to infection. There will be sterilization problems in continuous cultivation. So the same repetition. So these are the different phases of batch cultivation. Lag phase is nothing but the most initial phase where the organism, that is the inoculum, prepares itself for the new environment. And growth phase. The growth phase is further classified into three different phases like accelerated growth phase, exponential growth phase and decelerated growth phase. And the next phase is the stationary phase, and finally it will reach the death phase. So this is the typical graphical representation of growth phases, different growth phases, in which the x-axis represents the time and y-axis represents the number of cells at each particular interval of time. So ln x is the number of microorganisms present at that particular time. So when the time increases, what happens is the number of organisms will be prepared. The number of organisms will be at a constant state. Then suddenly at a particular time, it will rapidly increase, and that phase is the log phase. And when it reaches the stationary phase, it will be a stationary one, and after the death phase again the graph declines. So these are the three graphs. The first graph represents the time versus ln of number of microorganisms. Second graph represents time versus number of microorganisms, and the third graph represents the time versus net specific growth rate. So lag phase is nothing but the initial period of cultivation during which the change of cell number is zero or negligible. The lag phase is affected by several different factors. When the cells are placed in the fresh medium, the intracellular concentration of cofactors, amino acids, ions will decrease, and these have been synthesized and transported before the cell division to occur. So this is just a preparatory phase for the inoculum to enter into the log phase, and many enzymes have to be produced for its metabolism. So when cells are placed in medium containing several carbon sources, so what happens is if the medium has contained glucose and dextrose and sugars, and if we have several carbon sources, the inoculum has to prepare its body to produce the enzyme to metabolize the particular carbon source. So it will be having different lag phases for each source of carbon. So different single inoculum will have a single microorganism will have different several lag phases based on the number of carbon sources present, and this is called deoxy growths. So when glucose and lactose are present, then glucose will be utilized first, then lactose. So during the utilization of glucose, there will be one lag phase, and then it suddenly abruptly stops, and then again after lactose utilization, it will be moving to the again another lag phase. So how can we avoid lag phase? So it is not a productive period, it is a waste of time, just it will get prepared. So how can we prepare, how can we avoid lag phase is that we have to identify the inoculum stage. The inoculum has to be uh, incorporated into the bioreactor during the exponentially growing phase. Okay, so the exponentially growing cells have to be inoculated into the bioreactor. And the size of the inoculum. If the size of the inoculum is very large, then the lag phase can be minimized. So generally 10% is used for yeast and mold and 5% for bacteria, when medium of inoculum should be the same as that of the production medium. In certain cases, such as recombinant E. coli can also be used to reduce the lag phase. Then the next one is accelerated growth phase. At the end of log phase, when growth begins, the division rate increases gradually and reaches a maximum value. The specific growth rate increases to maximum during this phase. And exponential growth phase is nothing but like exponential phase. So it is given by the formula dx by dt is equal to mu x, where mu is the specific growth rate and x is the cell drive rate. So rearranging the different this and integrating this equation from the 0th time to a particular time of lag phase, and x naught is the initial inoculum concentration, that is microorganism number of cells, and x is the number of cells at a particular time t. So if you integrate this equation with these ranges, so we will get dx by x integral x naught to x equal to mu into 0 to t dt. So after integrating, we will get x is equal to x naught e power mu t, and td is equal to ln 2 by mu m. Td is nothing but doubling time. That is, initially if you give a particular number of microorganisms, and after a particular time it will double. So that time is the doubling time. So that can be calculated by using the formula ln 2 by mu m. Mu m is nothing but the maximum specific growth rate. So sometimes the doubling times for cell number and cell drive may differ as a result of non-constant cell mass per cell. If the growth rates calculated based on these are equal, then the growth is said to be balanced growth. So in the balanced growth, the composition of the cell is equal. So the balanced growth will occur where adequate supply of nutrients is there and no toxic byproducts are generated. So this is a balanced growth. In the case of unbalanced growth, there will be excess protein content or other unwanted metabolites are produced. So we have to need to have a balanced growth. So other phases of growth, immediately after the log phase, it will move to the stationary phase. This is the phase where the microorganism is getting depleted of nutrients and toxic metabolites will get accumulated in the system. So this is a phase where the cells will be alive, but the number of cells won't increase. So this is the stationary phase, and following this is the death phase, where the cells will start to lyse and the cell density decreases. So what are the environmental conditions affecting the cell growth? Is substrate concentration, temperature, pH, dissolved oxygen and others. So substrate concentration. The effect of substrate concentration, that is the glucose concentration or the nitrogen concentration, is represented by the Monod equation. Mu is equal to mu max into S by Ks plus S, where mu is the specific growth rate, mu max is the maximum specific growth rate, R and S is the substrate concentration, and Ks is the saturation constant. This is a derivative which is we are getting. When the substrate concentration is very higher on Ks, mu is equal to mu max. When S is equal to Ks, mu equal to mu max by 2. Thus, the saturation constant Ks is numerically equal to the substrate concentration when the growth rate is half the maximum. Then effect of temperature. The microorganisms grow at different temperatures. Based on their growth in different temperatures, they have been classified into psychrophiles, mesophiles and thermophiles. Psychrophiles are organisms which grow at a temperature of below 20 degrees Celsius, and mesophiles grow in the range of 20 to 50 degrees Celsius, and thermophiles grow at at a higher range of 50 degrees Celsius. So based on that, we need to supply the temperature. And temperature growth rate is explained by the Arrhenius equation. Mu is equal to A e power minus E by RT. Mu is nothing but the net specific growth rate. So temperature also affects the product formation. And effect of pH, as like in temperature, pH also plays a major role. So some will grow in the acidic pH, some in the neutral pH, and some in the basic pH. So based on that, the media has to be prepared. And dissolved oxygen concentration, this is a very crucial factor in aerobic microorganisms and may be limiting in certain cases. Oxygen is sparingly soluble in water, and the cells will uptake oxygen from the medium only. Dissolved oxygen concentration should be above 20% for bacteria and yeast, and it is 40% for moles based on the size. What are the other factors which affect the growth is that redox potential, ionic concentration, and dissolved carbon dioxide formation. And the product formation kinetics is given by Ludicky-Pyrrhic model. These are the different methods of product formation. That is, as the time increases, the substrate concentration, the cell mass concentration in the product formation increases as in the case like a growth rate, and or they are linearly same. But in some cases, as the time increases, the product formation is independent of the cell mass concentration, and in some cases, as the time increases, the cell mass concentration follows the growth rate, but the product concentration will be very late. After longer time, it will start during only the stationary phase. Okay, so here the first graph, it shows the product concentration starts along with at the 0th time itself, the product formation will start. And the second graph, the product formation starts during the lag phase, but in the third graph, the product formation starts during the stationary phase. So most of the secondary metabolites are formed during the stationary phase, and it follows the third graph. And this is the Ludicky-Pyrrhic model, growth associated products with respect to the microbial growth. So we have seen the three graphs. First one is the non-growth associated product formation, the stationary phase. At the stationary phase, when growth rate is 0, so antibiotics, most of the secondary metabolites will be produced at that phase. So first one will be the growth associated products are simultaneous with the microbial growth, and mixed growth associated, it will be in between the growth and the non-growth. And these are the different equations which follow this. Then, what is a continuous cultivation? As we have seen, it is a closed system. Batch cultivation is a closed system, but continuous cultivation is a open system. So the inoculum or the media components is fed as an open system. So in this case, the steady state is the condition at which there is no change in the concentration of biomass, substrate, product, or none. How will you say that the culture is at a steady state? When there is no change for two volume, change of medium, then the culture is assumed to be in steady state. So how will you dilute the medium? Dilution rate is the ratio of feed rate to the working volume. So how much feed you are giving when compared to the working volume is the dilution rate. The actual growth rate depends not only on the volumetric flow rate of the medium into the reactor, but also on the dilution rate, which is given by D is equal to F by V, where F is the feed and V is the volume, working volume. And this can be identified by the formula. The net change in the cell concentration over a period of time is given by dx by dt. That is rate of growth in reactor and rate of loss from a reactor. Under steady state condition, rate of growth is equal to rate of loss, and finally we'll get mu is equal to D. That is net specific growth rate is equal to dilution rate in the continuous cultivation process. Why continuous cultivation is not used in industries? Secondary metabolites are produced only during the stationary phase, and hence the continuous most of the industrially important products are secondary metabolites. So continuous cultivation is not suitable for the industries which are in need of secondary metabolites, and maintenance of sterility is very difficult, and high infrastructure cost is required. So Next one is fed batch cultivation. Batch cultivation have low productivity, whereas continuous cultivation have high productivity, but we cannot aim for secondary metabolite. So we follow a fed batch cultivation, that is a semi-open system, which is an intermediate between batch and the continuous. Here the nutrients are fed slowly into the medium, either continuously or discontinuously in different stages. So these are the different cultivation kinetic methods for different types of fermentation. Thank you.